as I was saying, sensors have 6 functions. The first and primary, of course, is to protect humans. Okay, and so there's various different sensors that are dedicated to those types of uses. We'll look at some of those and discuss some of those. They're also used to protect the robot, to collect data, to monitor the system for malfunctions, to provide some sort of measurement, or to monitor various parts and or to identify those parts. Okay, so those are our 6 functions. Okay, and then as I mentioned before, we can group these into 2 categories. They can either be of a contact nature or non-contact nature, and they can also have 2 types of signals. Those 2 types of signals are discrete sensors, which is really what we're going to concentrate on today, or analog sensors, which is what we're going to talk about on next Thursday. Okay. So for a discrete sensor, discrete basically means digital. Okay, so most of the time discrete and digital can be used interchangeably in a lot of cases. And so basically what this means is that it's either on or off, or sometimes we use the term high or low, or a 1 or a 0, because technically inside of the robot controller, all right, the robot controller really is just a computer. It's a digital computer. And so therefore everything inside of that computer, that controller, is a 1 or a 0. Okay, so so on, off, some true, false. I don't have true, false here on the slide. It didn't update again, did it? Yeah. Okay. All right, so I've been told that sometimes if your connection is not a real strong connection, it'll like drop you out. So I see like one of you just reconnected there. So sometimes if your internet's connection's a little slow, that might have an effect on that. Okay, so I am not sure why PowerPoint doesn't like to update and collaborate. This is kind of annoying here. Let me see about making it a PDF and see if the PDF will update. Okay, so excellent. So I've got a PDF here. Let me share the PDF, and maybe it'll update as I go along. All right, so we have talking about discrete signals here. So hopefully this looks like it's keeping up with me. Sorry about that. So discrete signals are digital in nature, or they're an on-off. If you think about like parts coming down the line, so the robot's going to be there and it's going to be picking up parts as they come down a conveyor line. So what you're looking at is a sensor sitting there, and as the part comes along, the part either hits like a switch along there, or if it's a non-contact type, it just senses that the object is passing by, and it becomes a 1. And then as the part moves on past that sensor, then it would go to a 0. So what you get is this digital signal here, where you have a low or 0 or off, and then an on. So when it's high, when it's a high, it's a 1 inside of the controller. So the controller is actually reading a 1. Okay. And so 1 normally indicates that something is there. And then when it moves on down the line, it goes to 0. And as another object comes along and it triggers the sensor again, it becomes a 1. So this is what we call a digital signal, on or off. Now, technically, those sensors, okay, what we're really looking at is a voltage. So those sensors are basically sending into the controller a high voltage or a low voltage. So that high voltage depends on the type of controller or the type of input that you have. Typically, for industrial applications, we have AC sensors that would output 120 volts. So when the object was there, it would send 120 volts into the digital input card within the controller. On the other hand, if it's a DC signal, typically at industrial levels, we use a 24 volt. Okay, so those for industrial applications are the most common. Okay. This is just a little sensor chart here, kind of showing you the different, try and zoom in on this a little bit. So it's just kind of showing the various different types of sensors. So we have contact sensors basically are limit switches, and we'll look at a few of those. Non-contact sensors fall into 2 categories, either photoelectric or proximity. And then there's also what they refer to as process control sensors, which, you can kind of argue whether these actually meet contact or non-contact there. So it's really almost a third category I didn't have on that list before. But these detect various things like temperature, pressure, the flow, whether material's flowing through a pipe or something like that, or possibly the level in a tank. Okay, so all of those could be digital sensors. So they basically, what would happen is, like for temperature, I mean, there's always a temperature, right? The temperature could be 28 degrees Fahrenheit or 212 degrees Fahrenheit or anything in between, or even above or below that. So temperature could be anywhere. But when we're talking about a digital sensor, we're talking about the sensor has a fixed value, and let me say this correctly. So there's basically like a threshold. So once the temperature gets above that threshold, then it would send out a 1 basically to the controller, or a high voltage. Okay, 24 volts if it's a DC digital sensor. So it'd send out a positive 24 volts to the controller if the temperature was above whatever particular threshold that sensor was set for. If it's below that, it would be sending out 0 volts. Okay, so anyhow, these are just some of the various different types of sensors for digital sensors, and then they would go into a digital input card that would be part of the controller usually, or it could be a separate like input device, and then it maybe goes to the robot through an Ethernet connection or Profinet or DeviceNet sort of network connection, and is sent to the robot controller. All right, so talking about the various 6 different functions of these sensors. The first one, as I mentioned, was, it's used to protect humans. And so what this picture is showing is a light curtain. All right, and so if we were in the classroom, I could like point to these little yellow bars on the robots in the classroom, right? And basically what happens is these send these little infrared light beams across. We can't really see them in the classroom, but they send these little beams of light across. And the idea is that if you stick a body part into the area of the robot, you have to go through this beam. And so when you cross that beam, it detects that light that's being sent from the transmitter. One of these is a transmitter transmitting over to the receiver. And when you stick your hand in there, now the receiver is not detecting on at this particular area. It's detecting that light being sent across got deflected and is not coming in. And that's how it knows that, somebody has moved inside of that work cell. Okay, so obviously there's nothing here that prevents you from sticking your hand or your head or something within that work cell. But what's going to happen is that this sensor is basically wired into the emergency stop circuit. And so if you break this beam, it causes the robot and all the equipment to go into an emergency stop condition and immediately stop running to prevent injury. Okay. All right, other limits, or the other function, the second function is to protect the robot. And one of the things that we do there is to protect the robot, is to keep it from going into an area that it's not allowed, because there's something in the way that it may either damage a robot or damage something else within the work cell. Now, the first method that we actually have in the robot to prevent it from going beyond a certain range is something called a soft limit or an access limit. So inside of the software, we could set up access limits that'll prevent the robot from moving too far in a certain direction. And so if it starts moving and the robot knows what angle or what rotation that arm is at, and if it goes beyond that, then the software should actually stop it. Okay. But as an extra precaution, we can throw in a safety switch. So if the arm moves too far, it presses against that switch and therefore stops it. So this is what's referred to usually as a limit switch. And so it's got this arm on here. And so what happens as an object, whether it's a robotic arm or we also use these on conveyors, where just to track as a part comes down the line and moves across, then it moves this arm, and this arm will fold down then. And so as that arm folds down, it then turns the switch off, sending a 0 to the controller. Okay. Or it could go the other way. As the arm goes down, it may send a 1 to the controller. So we actually have the ability, for most switches, you can kind of set them up to be, if you've had PLC class, which I think some of you have already had, you talk about normally closed or normally open. Okay, so a normally closed type of switch is sending a 1 normally. It's sending a high to the controller. And then when you activate the switch, you're actually breaking the connection and sending a 0. Okay, so normally closed would mean that we're actually going to we're sending in a high signal into the controller. And so, like, if we go back and we look at this, emergency stop type switches are wired as what we call normally closed, which means that we're looking for a 1. So this has got to be a 1 here. So all these all these light beams are sending out and triggering a sensor and saying yes, 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 yes. And then if you break that beam, one or more of these are going to report a no and send out a 0. And then that's what the robot senses to say, hey, I'm missing input. That sounds like a error, and I'm stopping and I'm turning on the stop. Okay, so that would be a normally closed. Like I say, emergency stop buttons always use a normally closed sort of thing because they're looking for that high voltage. And for whatever reason, if that high voltage disappears and it goes to a 0, then hey, there's a problem. All right, so even if it wasn't actually a person breaking through the light beam or some sort of true emergency, but just a wire got broke, vibrations and the wire broke or came loose from the terminal connection, all of a sudden, boom, you're going to go low, and now there's a problem. You're going to stop until you correct that problem. So it's so that's why we wire those as normally closed. All right, but other types of sensors, a lot of times we have the choice to wire them normally closed or normally open, depending on how we want it to behave. Now, the other side of that is, I'll show you later on when I pull up the RoboGuide software, is let's say that you went and you wired this particular sensor as a normally closed, so it's always putting out a 1 when there's nothing there, and then when something comes, it goes to 0, and that's backwards for you. Well, in the software, we can actually configure that input to reverse that input. So when the sensor is sending in a 1, then the configuration inside the robot's going to say, well, a 1 coming in means a 0, and a 0 coming in means a 1. So I'll kind of show you that here a little bit later. All right. The other thing to kind of help protect the robot or items within the work cell is a mechanical stop. So a mechanical stop is just putting something in the way that's going to just prevent the robot from going beyond that point. All right. So which means the robot's going to come over and then it's going to hit that stop and then it can't move any further. So really, the idea is to have it in this order, so the software should limit it before we get to the physical limit switch. Okay, but if it doesn't, then you got the limit switch and it should tell it to stop. And if that doesn't work, then we're going to physically hit this mechanical stop. But really, hitting that mechanical stop is not good for the robot. And so it's kind of just an emergency last resort sort of thing. All right, so one of the other items that we have the sensors for is, of course, is to simply collect data. So we might be simply using it to count how many products are moving down the line. So we may have various products going down, and we're just simply trying to keep count how many are moving past. So this here is actually a photoelectric sensor. So this is a non-contact type sensor. And you see here it looks like it almost has 2 little eyeballs. Looks almost like a robot itself or something. But basically this type of sensor, the way this works, one of these little lenses here actually has a transmitter. So it's going to send out a light beam. And then what you would do is you would take this reflector and set this reflector over here. And so the transmission of the light beam, we send out a light beam, it hits the reflector, reflects back, and the other one of these is actually just a sensor looking for the reflection of that light beam. And so if a part is moving down, the part would move between this actual sensor and the reflector. So the part would be moving down here in between them, and it would break the beam as it crosses that point, and then it would, the sensor then would send a 1 or a 0, depending on how it was configured, into the robot, and we would know that something is there. And so we could use that to simply count how many objects are going down, or you could also use it to indicate to the robot to stop the conveyor, come over, pick up the part, and put it on the pallet, or whatever the task may be. All right. The other type of sensors are, we're on number 4 here. The fourth type is to kind of monitor the system for malfunctions. And so in this case, the sensors shown in the diagram, these are actually current sensors. So these, you can see here, if I zoom in a little bit, these are to measure DC current. Okay, and so what they do, can't quite read there, it looks about 500 amps. Okay, so these things are really designed to read very, very large current, and like a big DC electrical motor or something. And so what you do is you just clip this over top of it, and you basically uses Faraday's law that says if you have current running through a cable, it's going to generate a magnetic field. And so then what we're doing here is we're actually sensing the magnetic field. So you run the power cable going to the motor, you just clip this over that power cable, and then it's going to measure that sensor, and then it's going to output a value into the controller. Now actually these sensors that are being shown here, it's kind of hard to read there, but it says 4 to 20. Okay, that's a 4 to 20 milliamp signal. So actually these things are analog sensors we're actually looking at here. They're not these sensors that they're showing in the picture are actually analog. So they'll give us a range of current from zero to 100 amps is what this one on the left looks like it's saying. And so what that means is if it's sensing 0 current flowing, it'll output a 4 milliamp signal into the controller. If it's sensing 100 amps, which is the maximum for this transducer, then it's going to output a 20 milliamp. And if the current is anywhere in between those two, it'll output something between the 4 to 20 milliamp range. So this is actually an analog sensor, but you could set it up to just trigger as, yes, the current's too high or something. So let's say that you only could handle 50 amps on your motor. So if it started hitting 50, 51 amps, you could have it set up in your controller to, to basically shut down, so we can figure out why it's drawing so much current. Okay. Another function of the sensor is to provide measurement. All right, and so this is various different types of sensors can actually do measurement. Again, most of these measurement type sensors are actually going to be more of an analog nature. Okay. And then the sixth function is for part identification. All right, and so one of the most obvious for those is simply scan codes. All right, so you have barcodes or various different types of scan codes that you can use to identify a part and identify its location. All right, so given that, those are the 6 sensors there. Okay, so we're going to talk here about 2 types of sensors. for the contact or non-contact type. And so those contact means that you physically have to touch the sensor. So whatever object it is that is doing the sense that you want to sense, that object actually has to come in contact with your sensor. Now, hopefully it's pretty obvious that the issue with this might be that since it's got to make contact, it may wear out. You've got moving parts in that switch, and so it's going to, it could possibly wear out. Okay, so that's a bit of an issue there. And also, obviously, if the part isn't quite close enough to make contact, or maybe it makes contact, but it doesn't weigh enough to trip the sensor, then you don't sense that it was actually there. All right, so one of those, as I say, is a limit switch. The other one is a tactile sensor. And I've got a video of a tactile sensor that I might try to play a little bit later. I don't know how it's going to play over Blackboard, but if it doesn't, I can at least share the link. It's just a YouTube video on there. All right, so here's just some pictures of some different limit switches, which of course are contact sensors. And so if I zoom in here on some of these, you can see like this one here is kind of a really small reed type piece coming out here. So as I was talking about the weight of your object when you're trying to sense it, if it's really light, then you got to have something that it'll be able to move. And of course, you don't want to damage the parts that you're trying to sense either. But some of these other ones are heavier. They could handle, you know, you see some of these arms and things here are kind of very large. And so they can handle more heavier objects on there. And a lot of them have wheels. So as the object comes along and hits the wheel, you know, the wheel will spin a little bit and then the arm will kind of get pushed over here out of the way. But the wheel, instead of it dragging across the part, it allows the part to kind of roll along it and try to, you know, not do any damage to the part while we're trying to sense it. Okay, so those are just various different types of limit switches. As you can see, there's just tons to choose from. Okay. Right. So here is kind of a breakout of how this works here. You have a receptacle box, which is just to kind of protect the internals from dust, dirt, moisture, anything like that in there. So you have like the mechanical arm piece here that is going to actually do the movement. And then you have the operating head, which is making the contact in here. And then you have your wiring coming in here that you're going to run out the bottom of the box over to the controller. All right, so when we talk about these contact sensors especially, and we saw that box on the previous slide there, they have what they call enclosure ratings. All right, and so these enclosure ratings are rated for different types of applications. So I just have a couple of them listed here just to be aware of it. I don't really expect you to memorize that NEMA 12 is dust type but not waterproof, but you know, I just kind of wanted to show you. So NEMA is the national code settings for these. Okay, so officially NEMA stands for National Electric Manufacturers Association, and they work with some others to set these various different types of standards. Okay, so so you should be aware that NEMA is used to set standards for enclosures. So like if the closure, if you were putting this switch outside or somewhere where it's going to get wet, maybe in a car wash or something like that, anywhere where it might be getting wet, then obviously a NEMA 12 would not work because it's not waterproof. And so that's just where, you know, so when you're deciding what you need, you got to keep those various thoughts in mind. You know, is it going to get wet? Is it going to be dusty? Is it going to have corrosive sort of materials that on it? Those sorts of things. Okay. And then when we talk about the switch itself, it's going to have contact ratings in there. And so it'll have both possibly a current and a voltage rating that you have to be concerned about, because you might buy a box that's only good for 24 volts DC and you're trying to use it for a 120 volt AC application, then obviously you know, you wouldn't be following code. So you need to make sure that the box follows it. So this slide here just shows an expanded list of the NEMA definitions and things. Again, I'm not going to expect you to know these. I don't remember these. You know, if I'm looking for something for a particular application, I just go look it up, right? That's what, you know, Google will or get you to a verified page that has these, and so you can decide which one's going to meet your needs. So again, I don't really expect you to memorize all these definitions. I'm not going to ask detailed information about these. I just want you to be aware of the fact that they exist. Okay. All right, so this here is just kind of showing the contacts for the sensors. These are really heavy duty commercial type contacts. As I mentioned before, they have both a current and a voltage range on them. So you also have to be concerned with how much current and how much voltage you're working with on these to make sure that they don't wear out or burn out after 2 or 3 uses. All right, so when we talk about the switch, okay, it's the switch. I kind of already mentioned this a little bit. The switch can be either normally open or normally closed. So basically what happens here is that you have the voltage, whether it's a 24 volts or 120 volts or whatever, that's coming in here. You don't really see it. Those are the wires coming into the box. All right, and so right here, you've got this arm on the limit switch here that's going to move. And this arm, you see right there, that screw, this arm is attached to the pole. So when this arm moves down, then this pole is going to come over here. Right now it's making contact up here where it says NC for normally closed. But as the arm gets pressed by the object coming down and the arm swings down, the pole is going to move away from the normally closed and come down to the normally open. So they call these the throws. Okay, so the pole is going to move from the normally closed throw over to the normally open throw. All right, now in this picture right here, I have one pole. It's possible you could have multiple poles. So this configuration up here is talking about the number of poles, P, and the number of throws. So in this case, this switch shown down here, I have one pole. So single pole, SP, single pole, but 2 throws, double pole. So this is a single pole, double throw switch. Okay, so you can buy switches that have single pole and only 1 throw, or a double throw as shown here, or maybe you have one that's actually got 2 poles and 2 throws. Okay, and so you could have a double pole, double throw, or double pole, single throw. So that's what that configuration reference means. Okay. So NC means that's the one that is normally closed, and so that's going to have a high voltage to it. So basically here we just have our voltage, whether it's a 24 volt DC signal or 120 volt if it's AC, or possibly for some sensors it may only be 5 volts or something. But it'll be a high voltage coming in here, and then that high voltage then is being applied to the normally closed. So if you wire the normally closed connection, then when nothing is there, it's sending a high to the robot. If you wire to the normally open, then as the part comes and it pushes the pole down, it's going to push that arm down, and which moves the pole down and makes contact. So when the part is there, we send a 1 to the robot. So we can wire either one of these into the robot. This slide's just showing some different rocker arm. This is called the rocker arm sometimes, this arm that's moving the pole. This slide's just kind of showing how it's going to move as you have an object coming down here. In this case, we've got an object with a bit of a angle to it, so that the wheel on there will roll easily across it as the part moves along. All right, so another type of contact type sensor is called a tactical sensor. All right, so this type of sensor actually is a whole bunch of them connected together. And so it's, instead of just having like one sensor there, you've got like a whole array of these sensors in here. And so the idea now is that you can detect part, you're more than just detecting yes the part's there or no the part's not there. So if you see here in this, here is this object we want to try to grab with these grippers, right? So we have a finger gripper here, kind of like the one I passed around in class, but this one here actually has a built-in sensor. And so it's got this grid on here, so each one of these grids are making contact. And then I have this triangular shaped object with a hole in it. And so as the gripper comes over and grabs the object and it makes contact with this side right here, and of course with the other side, and so now these sensors now, if you're making contact, they have pressure against them. They go, they're showing dark here as if 1. So basically the grayed out areas indicate that, hey, we're sensing that triangular part here. But these 4 in the middle are reading 0 because they're right there where that hole is in the object. All right, so if you guys have any questions at any time, be sure to be sure to just put it in the chat window there, or use the raise hand piece at the bottom of the screen or something. So, all right, so this is the tactile sensor, an example of a tactile sensor here. They're doing a lot of work with these. Most of these are actually analog. So not only do they detect that yes, it's there or it's not there, but they can actually detect how much pressure. And that's what that video that I have, I'll show a little bit later, shows you. All right, so looking at non-contact type sensors, those fall into 2 categories of proximity or photoelectrics, and then proximities can be broken down into inductive or capacitive. All right, and so I don't know if some of you may have already had DC circuits or something. Some of you maybe have not. But basically, an inductive sensor can detect metal objects, because what it does is it's kind of like that current sensor we looked at earlier. It basically relies on Faraday's electromagnetic principle. And so a moving piece of metal will induct current into this inductive sensor. So let me flip ahead here. I'll come back to maybe those slides in a minute. But what happens here is your sensor, okay, this is your sensor right here, and your sensor is made up of a coil of wire. Okay, so there's a coil of wire going around in the sensor, and that we're putting current through that sensor. And so as current is moving through that sensor, it's generating a magnetic field. So these angled lines up here are kind of indicating that magnetic field. So this coil is generating a magnetic field. Now, if an object is moving down past this sensor, so you have some object moving down past this sensor, this object is going to induce the magnetic field is going to induce a current into this metal object. Okay, and that current in there, it's not a huge current, it's very, very small. They refer to this as eddy currents. And so inside of that object of metal, you get this little electrical current just flowing around inside of that block of metal that's moving down the conveyor. All right, but because it's inducing and making those electrons move in that piece of metal, this coil is kind of senses that more current is required. All right, so as this object moves within this magnetic field, you start pushing these electrons around inside of this metal object, and that requires more power from the coil. And so there's a sensor. I guess I don't have that drawing in here, but there's a sensor further down inside here that senses that more current is being used inside of the coil, because you're basically lowering the resistance. And so that is what actually then sends the trigger to the controller saying that, hey, I just sensed that the object is there. All right, so again, without the object there, it's generating this magnetic field by pushing current through here. But when the metal object comes inside the magnetic field, it basically lowers the amount of resistance within this that it's taking to cause this magnetic field, and it draws more current, and that then triggers the sensor to send a 1 to the robot to tell it that there's an object there. The object is here. So this, the nice thing is that the sensor doesn't actually have to touch. Okay, so the inductive proximity sensor doesn't have to make physical contact. The object doesn't have to make physical contact. It just has to come in close. How close? Well, I actually had that in the previous slide. So it's got to be pretty close. The range could be 0.5 millimeters to 40 millimeters. And 40 millimeters, that's a couple of inches. 25 millimeters is about 1 inch. So a little less than 2 inches away. All right, so you got to be kind of close with it, but it can detect a metal object. All right. It cannot detect human skin, plastic, water, anything like that. It can't detect. It must be something that's going to react or that is going to modify that magnetic field in a drastic way, which means basically some type of iron, possibly nickel or cobalt, so some sort of metal. All right, these are just pictures of these sensors. The blue color that you see here is like the color, you know, like a trademark color from the manufacturer. It has nothing to do with the fact that these are inductive sensors and everything to do with the color of the company. So, you know, just like the FANUC robots are yellow in the classroom, right? That's their color. And that's more of a trademarked color. It doesn't, looking at these, you can't tell they're inductive because they're blue. All right, so a lot of these come in a little cylindrical form here. So you can just like drill a hole and put this in there, and then there's a nut on each side so you can screw it down and lock it so it maybe sticks out an inch or two, and that's it. All right, so inductive sensors generate magnetic fields. Okay. There's also capacitive type sensors. Okay, capacitive type sensors use a capacitor sort of electrical circuit. Okay, and they have some advantages and disadvantages. As you see right here at the sensing range, right? I guess a disadvantage of the capacitive sensor is you got to be no more than 15 millimeters. That's about the maximum range of a capacitive type sensor, and some of them are even less than that. All right, so remember the inductive one would go all the way up to 40 millimeters, which was near 2 inches, but capacitive, the max is about 15 millimeters, which is well less than 1 inch. Okay, so they have not quite as much range. However, they can detect liquids, solids, plastics, the human hand. So capacitive sensors have a much larger range. They can pretty much detect just about anything, any type of material, if it's close enough. So the capacitive type sensors here, now you notice these ones are orange, but again, that's the color of the manufacturer. You look at the shapes and sizes they come in. Looking at them, you can't really just look at it and say that's capacitive or that's inductive, because the boxes or the cylindrical sort of shapes they come in are basically the same. All right, so the way these work is they work as a capacitor. So if you remember capacitors, okay, capacitors, if you've had that, capacitors have two electrodes separated by what they call it, technically it's called a dielectric. But that dielectric basically just means an insulator. So that dielectric could be air, or it could be plastic, it could be paper. Okay, so there's anything between two metal plates. So you have these two metal plates, or what they're calling electrodes in this slide, and so you put a voltage difference between here, and it generates an electric field between the two plates. Okay, and so what happens then is, as an object moves into this electric field, it changes the strength of the electric field. And when the strength of the electric field changes, then the voltage on these plates will change right away. And so that's how this capacitive proximity sensor works. Okay, so so basically they use air as the insulator between the two plates. But if a piece of plastic or human hand or a bottle of water come down and enter into this field, then that affects the voltage on these plates. And so that sensor can then detect that, hey, that object has changed my voltage, so I know something is there. And that's how those work. Now, to wire these switches up, they're basically usually come with 4 wires. 2 of the wires are basically to power these things, right? So whether it's an inductive switch or a capacitive switch, you got to power this thing, right? So you got to put power on these at these points to generate the electric field. So you need to power it to generate the electric field or magnetic field if it's inductive. All right, so the blue and brown wires are your power wires. So you need to have some kind of supply to power these. A lot of times for industrial sensors, as I said before, they're 24 volts. So you need a 24-volt supply. And then there's a white wire and a black wire. Now, some of the sensors, maybe they only have a white wire or a black wire, but not both, okay? But a lot of them will have both. And basically what they are, the black wire, I should say it on this slide, but I don't. The black wire, if I remember correctly, is the normally closed. Or no, excuse me, the black wire is the normally open on there. So normally you're going to wire up the black wire, and that's normally open. So what that means is that if the sensor isn't sensing anything messing with its field, then the black wire is going to be outputting a 0. But at the same time, if it is a 4-wire sensor, the white wire is going to be outputting a 1. And then when the object comes into the field range and affects it, then the black is going to go 1. It's going to go high to a 1, but then the white's going to go to a 0. So you have actually both a normally open and a normally closed on some of those switches. It just depends on the switch whether they give you that extra wire or not. Okay, obviously to have 4 wires, it costs more than to build one with 3 wires, so it might cost a little bit more. So that's why they don't always give you all 4 wires. Okay. For photoelectric sensors, they basically come in 4 different types. One of those is called retroreflective, which means that you got to put you got to have a reflective surface. So as the on the other side of the thing. So that's the one that I showed you way earlier in the slides, and there was a reflector with it. Okay, so it sends out, and then it hits a reflector and reflects back. Another one is called diffuse reflective. Diffuse reflective, it sends out a beam and it reflects. It expects that beam to be reflected back from the target when the target is there. In general, the diffusive reflective don't have the distance range that the other ones do. Okay, so the retroreflective, you could have that part might be a foot away or maybe even several feet away. Okay, so one of the nice things about the photoelectric is they give you much further distance of sensing. So remember, the capacitive one was always less than an inch. An inductive one could maybe do almost up to 2 inches. But the photoelectrics, you can easily go 6 inches with a diffuse reflective type, depending on the type of the color and reflectability of your target. Or if you're using these retroreflective where you're sending out the beam and then the beam goes and hits a reflector and reflects back, there you could go 1 or 2 feet or maybe even more. Okay. And then the third one is a combination of these first two. And then the last one here is, it has instead of having the sensor on both, the sensor and receiver on both connected together, you have two different boxes. One is the transmitter transmitting the beam, and then the other box is the receiver. Now, one place I see these a lot, if you have an electric garage door, okay? So if you have an electric garage door opener, then at the base of the garage door, you have these here. So you have a transmitter box, and that transmitter box transmits that beam over to the receiver box. And that way, if somebody is walking through that beam when the garage door is going down, it triggers the garage door to go back up. This happens at my dad's house all the time. I go in there, I'm trying to shut the garage door, and his dog will run through the beam just when it's, the halfway down, and the dog runs through and triggers it, and makes it go back up. Okay. So, but the nice thing about these, here, this last one has a very large range. If you think about garage doors, typically they're like 8 feet wide. Some of them are even up to like 16 feet wide. So these beams, so you're talking 16 feet away. You're sensing anywhere within that 16 feet range whether something broke the wire or not, or crossed the beam. Not the wire, but the beam. All right, so photoelectrics have a huge sensing distance. It depends on which type that you have. They also use something called dark on or light on. Now, this is actually what I just discussed earlier about normally open and normally closed. But since we're talking about light, they use the term dark on or light on. So if it gets dark, it's going to send out a 1, meaning that, something broke the beam or it's not seeing the reflection. Or light on means it's going to be a 1. So light on is basically like normally closed, and dark on is basically like a normally open. So, but it's kind of a different terminology that you see with photoelectrics because they're talking about a light signal. Okay. The other thing is the response time. I guess I didn't really talk about the response time with the photoelectric. Not the photoelectric, excuse me, the inductive or capacitive proximity sensors, but they're kind of slow. If you got parts moving down at 1 a second, they can probably handle that. But if you got parts moving down the line at, say, 3 a second or 10 a second, I mean, if it's something moving very, very fast, they may not detect it. Okay, so the photoelectric sensors usually they definitely have much more distance, and they usually are going to respond much faster than the proximity sensors. All right, is everybody doing okay? No questions so far? All right, so looks like maybe this was the last slide. All right, so so that's the last slide there. All right, I did want to kind of share with you the RoboGuide software here. I've got it running on the computer, and I just kind of wanted to show you sort of what it would look like on the actual robot, okay? And so let me share that window. Get the right screen here. All right, so I'm going to share the RoboGuide, And I just kind of want to show you what the I/O looks like on this. Okay, so this is the RoboGuide software. This is the simulation software that FANUC provides at cost. It's not cheap software, but fortunately we get an educational discount on it here. But this this here is the I'm showing you the kind of the teach pendant here. And if we go to menu I/O, you can see your digital inputs and outputs here. So right now I'm down here on these inputs, okay? And if I flip over to configuration, you notice how like 104, there's nothing at 104, it's just stars. 101, 2, 3, 4, those are all starred out. But 105 is off. So if we flip over to the configuration, you can see here that digital input 105 through 144 is set up on slot 1 of the controller. All right, and so so it's configured where 70 through 104 is unassigned. And so that's why when we come back to monitor, we see these ones just have stars because they're simply not on. Okay. Now, I set this up the other day. Let me see if I can I don't know if, okay, can you see the whole screen now? All right. We can see at least most of it. So I set this up the other day that I think if I press Shift Tool 1, is it going to work today? Okay. All right. So I believe I have this set up so that if I go to the configuration, let me check my setup. So if I go to setup under macro, I created a macro that's hooked to digital input 105. And so what happens is when the digital input 105 becomes a 1, it's going to execute this program called clockwise. And so what's going to happen then is it just goes around this box clockwise. Okay, so that's what this clockwise thing does. So it just goes around the box. All right. But the thing is that you see here, it's set up that when digital input 105 is on, it will do that. So if I come back to my I/O screen, okay, I can simulate this digital. Okay, so I can come over here and I select on, and when I gotta come over here and tell it to simulate. So I'm going to tell it to simulate this. Since we're not in the actual classroom, I can't have it do that. So I'm simulating this input, and this allows me now to force it on. And so when I force it on, then it runs through this program. And I forgot I had that message up there. It says, "Oh, hello class." I was just demonstrating in the other in the industrial robotics class how to send messages, so that's why that came up there. But so you see there that when I trigger this and it goes on, that then executes this program. Okay, and it just goes around the box twice and outputs hello class onto the message screen. But I just kind of wanted to at least try to illustrate that for you. So you have whatever sensor is coming on. So if you have the idea here is possibly the you've got the object coming down. you got the object coming down the line, and when the object hits the sensor then triggers something on, and then you can use that then to have it, you know, go over then and pick up the object or something like that. So that's kind of where these digital sensors can be used. All right, so I got to get my mouse. It's really weird for me because I'm got this. I was moving my mouse and seeing it move inside the Blackboard screen, and couldn't figure out why I couldn't get out of the Blackboard screen. Okay, so all right. So one other thing here I was just going to try to share with you is if you look, I believe under lessons. Under Blackboard there, under week 9, down at the bottom, I had a link to the tactile sensor. And I'm going to try to share this screen. That doesn't look real promising here. So let me just pop this up into another window. Hello. All right, so it's loading. All right, so let me share this screen. Okay, so here is a example. It's already half done. Restart it here. But this is an example of the tactile type sensor here. So they kind of show you this here. And as you can see, as he presses on it, you can see it there. And as he presses harder, it gets darker. So this is actually an analog sensor. So the, you know, as it becomes more red, you can see how it's sensing and stuff. So this is some pretty cool technology. Again, you see the 3D presentation there. As he presses harder, it gives up more height. And look how he's using his breath there. Can you guys see that okay? No, I don't want to. All right, so hopefully you guys can kind of see that okay, but that, did it play?